and welcome back to another round of Steel Connect webinar. I'm Rocky and your host today to talk about steel and building related topic. So before we start, as usual, if you have any questions to ask during the session, feel free to drop it in the Q&A box on the side. All right, and of course, this is how you'll be able to find the Q&A box if you are joining us via your handphone. And for fellow architects and engineers, if you wish to claim your LAM or BM CPD points, please stay through the entire webinar. I'll share the QR code and also the link of the survey form at the end of the webinar. And you may submit your membership number via the survey form. All right, so without further ado, let me introduce you to the topic and also the speaker of the day. So the topic of the day is application of roof thermal insulation in tropical climate. And of course, this has to do with the roof systems per se, and how the subcomponent can help with tackling so-called the building warming up. So today is about that. And I'm honored to have architect Dr. Lim Chin Ho to join me today as the speaker. So Dr. Lim is, just a brief introduction. Dr. Lim is, the current Senior Research Fellow for Solar Energy Research Institute, or SERI, in short, in the University Kebangsaan Malaysia, or UKM in short. So of course, a brief, history of Dr. Lim. So he has over 30 years of professional architecture practices and academic experience, spanning from topics like passive and low energy architecture, and like building energy simulation and performance, energy efficiency, building insulation, indoor air quality, thermal comfort, and of course natural ventilation. So his past record and also current so-called positions includes the so-called as the assigned by United Nations Industrial Development Organization, or UNIDO, as the national evaluator for several national projects, such as the greenhouse gas emission reduction in targeted industrial subsectors through energy efficiency and application of solar thermal system in Malaysia. And of course, energy efficiency in terms of low carbon transport in Malaysia. Okay, so he has also served as the MGBC board member in between 2017 and 2018. And he's also the current head of the first authorized training center for this building performance simulation software called IESVE. Right. So in 2021, which is last year, he was also appointed as the expert for the Malaysia Sustainable Energy Development Authority, SEDA, to develop training guidelines for building energy modeling. So he was also invited as an expert panel for the working group to revise numerous Malaysian standards, which includes MS1525, which is for energy efficiency and use of renewable energy for non-residential buildings. And the second version of Malaysian standard 2095, which is for radiant barrier and reflective insulation in building, right? Material and specification. And of course, the last one is MS2680, which is for energy efficiency and use of renewable energy for residential buildings. So this is essentially a standard for code of practice lah. Of course, Dr. Lim has also received a very prestigious award for the ASEAN Energy Awards in 2004, 2014, and 15 for his work in the field. So without further ado, I would like to invite Dr. Lim to give us his presentation.
Okay, thank you very much, Rocky, for your kind introduction. and inviting me to share with you on today's topic on basically the insulation for tropical climate. All right, can I share my slides?
Yeah, yes, go ahead.
Okay, as we know, the topic for today's sharing is actually an application of roof thermal insulation in tropical climate. I will address specifically on the insulation, especially in our climate, which is a tropical climate, rather than other climate, which is temperate, which is not so relevant to us. I think tropical climate will be then more appropriate for us as we live in this equatorial region, right? Okay, the table of content. Today's presentation, basically I'll split into four main sections. First, I will talk about the background, about the climate, okay? And then we talk about the heat transfer through the roof and various type of thermal insulation and how does this insulation works, right? The second one, and we cannot miss, is actually to talk about the definition of these insulation materials and systems, and also the test methods. Then thirdly, we will zoom in into the radiant barrier and reflective insulation as one of the most effective insulation systems for our tropical climate. And we'll talk about the techno-economic analysis and a bit of animation on the computational fluid dynamics simulation on to show you how the heat transfer from the sun through the roof into the building, right? And last but not least is the conclusion of this presentation, right? Okay, as we know, the building actually consume almost globally 40% of the global energy. So building actually is very, very, very critical because we consume a lot of energy. So as an architect or designer, we have to be very concerned how to design our building so that the building can be very efficient and able to reduce this energy consumption, right? So by 2030, expect to increase even by 50%. Malaysia itself, the buildings consume 48% of the electricity generated in the country. So that is how significant it is for us to look critically and to address this problem. Okay, as we know, we cannot run away because the performance of buildings actually depends on the climate, right? So this slide shows you the Copenhagen climate groups. So this is the standards that we refer to the climate categories. Then you have tropical climate, you have dry and arid, you have temperate climate, you have continental, and you have polar climate, right? So if you look into Malaysia, we are at the tropical climate zone, right? If you look into countries like United States or even in Europe, then they will have more temperate weather compared to us. Of course, in certain regions in Africa, then you have various type of climate. You have dry and arid, you have even temperate, continental, and so on and so forth, right? All right, so climate has a very significant influence on the building performance. As you know, cooling is actually one of the main culprit, I would say, that actually require a lot of energy or consume a lot of your electrical energy, especially your air conditioning system. So air conditioning system, as you look into the data on your right-hand side, the International Energy Agency data shows you cooling take about 7% of the total energy consumption. So even some building consume more than that. Depends on the building design, but this is quite general, right? All right. So roof, in terms of roofing, actually it's very important to look into roof because compared to other building envelope system like wall and glazing and so forth, roof is one of the major. Why? Because we are located at equatorial. So the sun is always on top of us. So the radiation or the heat transfer comes from the top, which is the roof, especially between the low and medium rise building. Not high rise, of course, high rise, then the facade is the major component where you take in a lot of heat transfer, right? So it is 87% of heat entering into the indoor is actually through radiation or radiative heat transfer compared to conduction or convection. So that is how our heat been transferred into the internal building, internal space of the building. through the roof, right? So we have to address the insulation of the roof if we want to reduce the cooling load or the cooling energy of a building. All right, so for the why building insulation is so important is to reduce the solar heat gain, right, from the external environment, right? So with and without insulation, it plays a very significant. Without insulation, then you have money going out spending on your cooling. Compared to with insulation, then you're able to reduce the cooling, and even your sizing of your air conditioning system can be reduced. So that is how significant it is, right? So there are many types of insulation, but I would like to divide it into basically two. One is called the refractive, and the other one is called the mass insulation. I think mass insulation is quite common, as we know, like rock wool, mineral wool, polyurethane. These are all mass insulation. And the other one is reflective foil. It's actually made out of aluminum, because aluminum has a very low emissivity, 0.03, compared to other metal, although it's high conductivity, but it's also high in reflectance, which is make it a very good insulation. But it has to come into a system or assembly in order to perform as the building insulation system. Okay, how does these two types of insulation works? These slides will show you an overview of it. Okay, you look at on the left is the mass insulation, and you have the heat coming in through that mass insulation. It's actually trapped by the mass insulation, and that will slow down the conductive heat gain. Whereas the reflective foil is more of a reflection, that it can able to reflect the radiative heat transfer out. High reflectivity of more than 95%. And because also the other factor has a low emissivity or low emittance value, aluminum has 0.03 or less than 0.05. That means, in other words, it's able only to emit heat around 3% to 5% of max. So that's why it makes it a very good insulation. But it has to come with the system, with an air gap, because air is also one of very important what I call insulator, right? So in order for reflective foil to work, it has to have a reflective air gap. Okay, how does this insulation be installed in the roof? Okay, you look at the reflective foil normally is installed after the purlin or the roof batten, right? So it fixed underneath. That batten or purlin would then create a reflective air gap, so that this reflective air gap will able to reflect out the heat, the solar heat, or solar heat gain from the roof. And some installation, they do put actually on top of the ceiling. That will do as well. But the performance, of course, is not as good as the one that is below the batten or the purlin, right? That reflective air gap is more, what call the performance is better. Whereas the one that is facing the attic space, if you put it on the ceiling joist, then it will become a radiant barrier, more like a radiant barrier. And mass insulation, I think all of you have known, they are very what I call common, and normally they put also as an insulation, especially for the metal deck roof, because it will dampen the acoustic sound during the raining time. So that is a very common. Sometimes also they put it on the ceiling joist as well. Okay, so the factors that actually affect the performance of this insulation, actually one, of course, is the climate, which is we've been talking about. It covers the cloud cover index. Malaysia has a lot of cloud cover, very high, especially in the afternoon, and then humidity and solar radiation, and also ambient temperature. Besides that, the roof design is also very important. The roof design, the material of the roof, the thickness of the insulation, the insulation thermal resistance value or the R value, the emissivity or the reflectivity of that material, the air gap thickness, yes, the air gap, and the attic space roof, right? Okay, so that one will all entirely build up on the entire U value of the roof. The thermal transmittant, U value means the thermal transmittant. I will go to the definition afterwards in detail. The thermal transmittant of the roof actually make up of this climate and also the roof design. Okay, how do we measure the emissivity of the material? This is the ASTM C1371. It's an emissiometer that used to measure this emissivity of material. So aluminium has 0.03 compared to the common building material of 0.9, 0.8. So that is the difference. Okay, definition of emissivity here defined by these standards is called the ratio of thermal radiation from unit area of surface to radiation from unit area of a full emitter, which is a black body at the same temperature. For instance, the emissivity of aluminum foil is 0.03 to 0.05 at the temperature of surface in the building space, attics, or other habitable room. And this means that the material emits only 3 to 5% of the amount of heat that a black body would emit if it were at the same temperature. So that is the most material like wood, tiles, and so on and so forth have 0.8 to 0.9 emissivity. It means that able to emit 80 to 90% of the heat which will be emitted by a black body at the same temperature. So at the right corner, you can see all the list of all the common building materials and the emissivity, right? So aluminum foil at 0.04 or sometimes it's 0.03. So it's only able to emit very low percentage, which is 3 to 4%, the heat that actually been absorbed by the material itself, compared to brick is almost 90%, right? All right. So the other definition that we have to look in is actually the reflectivity. What is reflectivity? Reflectivity is the ratio amount of thermal radiation reflected from a surface that which falls on its surface. The aluminum foil has a high reflectivity of 0.95, which means it's able to reflect 95% of the incident thermal radiation, whereas the most common materials and surface of mass insulation have low thermal reflectivity, which is about 0.1 only. So you look at the graph, you can see that even the polished and the unpolished aluminum surface makes a difference, right? So you can know that the polished have high reflectance value. This graph has what I call x-axis is actually the wavelength in nanometers, and y-axis is reflectance. And 1 is 100%, 0.9 is 90%. So polish is almost 90%. Okay, so let's go into the definition of radiant barrier and reflective insulation. Most people are very confused about these two definitions. So people say, hey, radiant barrier is also reflective insulation. Reflective insulation also radiant barrier. But if you talk technically, you look at the NS2095, which is the Malaysian standard for radiant barrier and reflective insulation. It defines radiant barrier as a material of low emittance surface and when it's facing an open airspace. Okay, take note of the word open airspace. So that when the aluminum foil is facing open airspace, then it's called a radiant barrier system. Whereas the reflective insulation is a thermal insulation consisting of one or more low emittance surfaces bounding one or more enclosed airspace. So take note of the word more enclosed airspace with a measurable R value. You can actually measure that R value. All right. That open space is quite difficult to measure because attic space is so big. Even like even the hypermarket installation, the foil that facing the airspace is actually the whole hypermarket volume of airspace. So it's quite difficult to ascertain the R value. But in the reflective insulation, whereby it actually face the enclosed airspace, which is normally the batten or the purlin gap, the air gap, that one can be measured, the R value. So that is called reflective insulation. So I hope that is clear now. All right, this is some guideline from ASHRAE Handbook Fundamentals on Reflective Air Gaps. Actually, ASHRAE has a table that shows you various airspace thickness and also the heat flow direction and their thermal resistance values. All right, so this is a guideline that actually you can refer to. Okay, so this slide shows you a bit of more details of how the radiant barrier and also the enclosed airspace. The enclosed airspace is actually in between the aluminum foil surface, and also the metal deck roof. Whereas the radiant barrier is actually the surface, the aluminum surface that face the attic area. So it's called radiant barrier system, right? Okay, so you look into how to gauge this reflective insulation. It's actually, if you look at the formula, it's actually the total, the R value of the whole roof assembly is actually the R value of the airspace plus the R value of the attic airspace. Right, so the R value of the airspace is the T1 minus T2 temperature divided by the Q, which is the heat flow. And the RSI for the attic is T2 minus T3 divided by the Q for the attic. So this is the total roof assembly R value. Okay, and then another definition that we also have to take into consideration is the solar reflected index, or sometimes we call it SRI. So US Green Building Council, or USGBC, define it as a measure of constructed surface ability to cool, to stay cool in the sun by reflective solar radiation and emitting thermal radiation. So the procedure defines the SRI that measures the relative steady state surface temperature of a surface with respect to the standard white, which is the SRI of 100 means 100% of reflectance, and the standard black is SRI 0 under the standard solar and ambient condition. 0 means you are not able to reflect. Right? So the calculation of SRI are performed in compliance with the ASTM standard test method of E1980 for the measure value of solar reflectance and the thermal emittance. So you need two parameters so that you can able to compute the SRI, which is solar reflectance and thermal emittance. The program used for the calculation also is provided by this Lawrence Berkeley laboratory in California. Okay, so the solar reflectance values are normally measured using ASTM standard method E903, or hemispherical spectral reflectance measurement. You can use a UV vis NIR lambda 950 spectrometer by Perkin-Elmer. That one, I will show you a bit of the picture. I can give you an idea of the instrument that able to measure this solar reflectance. So utilizing the integrating sphere and thermal emittance values are measured using this ASTM test method of C1370 using emissivity. So for the emissivity, you have to use emissivity under the ASTM C1371. Okay, this is a picture of the UV vis NIR spectrophotometer that used to measure the solar reflectance. So if you have a roof materials like a metal deck roof or some coating that you want to see the solar reflectance, you need this equipment or instrument to measure it. It's under the ASTM standard of E903. Right? Okay, so the SRI calculation, once you have the solar reflectance and the thermal emittance of that material, you can actually calculate the SRI. I think this one is what I call Excel, in Excel format. You can actually download it from the Lawrence Berkeley National Laboratory. It's HTTP there. You can go in and download this software. It's an Excel anyway. It's quite easy to use. Okay, so reflective, these methods for measuring this radiant barrier and reflective insulation, there are basically three I would like to categorize. One is a laboratory measurement, which is using a hot box. Hot box is not so commonly now using because it's quite what I call take a long time to do the measurement. Currently, the most popular one is called heat flow meter. Only evaluates thermal resistant insulation material and not the whole roof assembly. Although it's equipment that able to measure, but it only measure the material itself, and maybe with the air gap, but it cannot do the whole entire roof assembly. It cannot go in. Then the other one is the solar simulator. Solar simulator is something new. I'll show you a bit of picture, and we have it in UKM. We do have a solar simulator to measure the roof assembly. All right, so these are the laboratory measurement methods. Whereas there are also methods using field measurement. So you build a test cell or small little building, then you put in the insulation material and you do measurement on site. So that will depends on the climate condition. If raining, you get to do a bit measurement. You have to wait for sunny sky for you to undertake a measurement. So the other one is computational fluid dynamics or computer simulation technique. You can actually model the roof, and using the computer technology, you can actually simulate the heat transfer and measure the R value or the U value of the entire roof assembly, right? So there's basically three methods. Okay, this is the picture of the heat flow meter I'm talking about. So this one is in UKM. This is the machine that's actually funded partially by GBI and also UKM, right? So it has a maximum thickness measurement of 180 nm only, with the two heat flux transducer, top and bottom, and it can have a bi-directional heat flow direction. So you can actually have a heat flow from top to bottom or bottom to up, right? So that is a heat flow meter. It's able to measure the thermal resistance value or the R value, and also the thermal transmittant value, which is the U value. Okay, this is the standard of ISO 8301 on how to use the heat flow meter, and it's quite similar also to this Malaysian standard of MS2095. Also spell out how to do the measurement with the boundary condition of 35 degree at the hot plate, and the cold plate is 20 degree. So the heat flow is going down at a temperature difference of 15 degrees Celsius. Okay, this chart is on the show you a bit of data on the reflective insulation using heat flow meter. So this chart show you the R value of the reflective insulation without any air gap. Okay, without any air gap, you can see that there are various types of reflective insulation here. We have a foam foil of 10 mm thickness, foam foil of 5 mm. Foam foil means it's a sandwich, it's a hybrid system. You have a mesh insulation in between, and then sandwiched by two aluminum foil, right? So the other one is a bubble foil. Bubble foil has a bubble wrap. It's something like the one protective wrap that you have from your Shopee or your Lazada purchase. You have the kind of wrap or the bubble, and then you have foil in between, sandwich in between. This is bubble foil. So there's bubble foil 13 mm and bubble foil of 10 mm. So without any of this air gap, you can see their performance is actually not good. The R value is only 0.23, 0.1, 0.15, 0.12, right? So if we put an air gap of, let's say, 50 mm to the material, to the foam foil, to the bubble foil, and see how is the thermal resistance value. You can see that the R value has jumped from even 0.1 something or to 2.47. So this experiment shows you that reflective insulation is a system. You need an air gap to perform as an insulation. Without that, it will not perform. Okay, so with that, you can see that the insulation has gone up to more than 2 of R value, which is very good, right? So this is the picture of the indoor solar simulator in UKM that we do the measurement of the entire roof assembly. Just now we know that the heat flow meter is only can measure the material and also a bit of air gap, because it has a constraint of 180 mm thickness from the machine. But this one, you can actually do a mock-up of the roof, entire roof, into the solar simulator, and then we can actually measure the whole assembly of the roof U value or R value. All right, so another methods that I'm going to show you is actually the 3D computational fluid dynamics. Okay, we've actually modeled the 3-dimensional of the roof in the computer software, or called CFD in generic name. And you can actually simulate the heat flow from the roof. The good thing about this is actually it shows you the graphical images of the heat transfer. Then you can see the temperature gradient, and in between without insulation, without reflective foil, and with the reflective foil. Okay, the picture on top, you can see that it's a lot of reddish color, and it shows you the roof that without reflective foil. You see the heat flow coming through, a lot of heat, right? The bottom one is the one that with the reflective foil. It shows you the reduction of the heat in graphical format. You can actually look at it. It's actually a lot of difference. All right. Okay, this is animation of another roof at 45 degree with that insulation as well. You can see the difference, right? The one that is bottom one has a insulation, therefore you can see a lot of more bluish color, right, compared to the one that's on top, which is without the insulation, a more reddish color, right? Okay, so I'd like to share with you a paper that has been published by Mario A. Medina and Brian Young. It shows you the performance of various types of insulation materials, especially based on the climate zone. Based on the climate zone, because I think US, there's a various climate zone from San Francisco, California to Miami. Well, Miami, of course, is tropical, as you know, quite similar to Malaysia. Compared to San Francisco, it's more temperate climate, right? So you can see that the performance of the foil becomes more effective, especially the heat gain reduction. You can see it in Miami, San Antonio, and Topeka. You can see the heat reduction during the summer is more, almost more than 30%, 35%. Whereas compared to Helena, Astoria in Oregon and San Francisco, it's only has a very low, able to reduce the heat very low, which is maybe California is only less than 5%, right? So that shows that the performance of reflective insulation is at least more suitable for tropical climate, or tropical high humidity climate, compared to temperate climate. All right. So another paper that I also would like to share with you is a paper that published by UKM itself, by myself, and my PhD students, and also GBI and Daryl in cooperation. We have run various configuration of roofing insulation system. We have the base case without the insulation, and we have other what we call configuration like glass wool, metallized foil, rock wool, metallized foil, small bubble foil, and big bubble foil, foam foil, double big bubble foil. And we want to see this what we call configuration if what happens if we integrate it into a typical hypermarket scenario. The scenario profile is actually using a metal deck, and of course located in Malaysian climate, and operation 1 year, 7 days a week, and we put in AC and also the lighting. All right, then our shoppers occupancy at 100% and so on and so forth. All these boundary conditions that we put in during the simulation, and we want to see the what we call the percentage of annual cooling energy reduction of various type of configuration of roofing insulation. You can see that the big bubble foil has almost 41% of the annual cooling energy reduction. This is done by simulation, and compared to even other type of insulation, maybe the type of insulation is also depends on the application. And rock wool is 36%, small bubble foil, aluminum foil is 38%, and big bubble foil is 39%, that kind of thing. All right. So it has a different performance of cooling energy reduction based on the type of configuration. Okay, so I would like to conclude today's presentation, and I want to just highlight back that the climate plays a very important role when it comes into a type of insulation that you apply on your roof. The climate such as solar radiation, the ambient temperature, relative humidity have a direct effect on the performance of the roof insulation. So as the study revealed that the reflective foil is, of course, more effective in the tropical countries or tropical climate like our country, with a high ambient temperature and high humidity all year round. So the characteristic of reflective foil, it has to be high reflectivity and low emissivity, which is able to perform as what is intended for. So mesh insulation is, of course, more beneficial experience, especially in the cold winter climate with extreme low ambient temperature. So the R value of mesh insulation is effective in reducing heat loss, thus reduces the heating energy usage, especially for the temperate climate. So with that, I would like to end my presentation. I would like to hand it over back to Rocky.
Hi, Dr. Lim. All right, thanks for your presentation. Yeah, so we would like to move on to the next section, which is our dialogue session, where I prepared a few questions to ask Dr. Lim. So as a reminder, of course, for our guest participants, if you want to ask your questions and to Dr. Lim, feel free to drop it in the Q&A box. Yeah. So Dr. Lim, my first question is about the practicality of so-called the reflective insulation, or so-called the reflective air gap. So of course, I think without a doubt, we both agree that insulating a building is crucial to maximize the energy performance of the building. That's for sure, right? But the method of insulation can come in many forms. As during the preparation, we did see anticipation of different types of configuration. But in your view, for the reflective air gap, what is the practicality of introducing such gap? Right, and also, is it currently being practiced in the construction industry in Malaysia?
Okay, thank you, Rocky, for the question. Of course, reflective air gap is required and is actually in the practice. If you install reflective foil, you are you are required to provide a reflective air gap in order for the reflective insulation to perform. So reflective air gap, as what I mentioned in the presentation, is that actually the air gap in between the aluminum surface of low emittance value, in between that what I call surface, and also the roofing material. So that is called the reflective air gap. So normally the reflective air gap is non-ventilated. Non-ventilated. So for it to be what I call a reflective air gap, for it to function, so if you have the aluminum foil that face an open airspace as defined by the MS 2095, then you call it a radiant barrier. Radiant barrier. It also can perform as an insulation system, but of course it's not as effective as compared to the reflective air gap. But having said that, of course, in terms of long-term performance of the aluminum foil, is also subject to the what I call the installation location. I'll give you an example. Let's say you install this reflective insulation in a very dusty environment. For instance, it's a factory that produces furniture, wood furniture, for instance. You have a lot of dust. Dust accumulation will also can lower the performance of the reflective insulation by increasing the emissivity of the foil over a period of time. So hopefully by doing the reflective air gap, you were able to conceal as much as possible that air gap from dust from going into it and sticking onto the foil surfaces or the aluminum surfaces. Okay, so that's very important. So in order for it to function, that you have to really conceal it properly. By concealing, also you are reducing the heat loss or the heat transfer by convective, because it actually minimize the airflow into the reflective air gap.
Yeah.
So that one is also very what I call important consideration when you do reflective installation. Okay.
Thanks, Dr. Lim. Well, moving on to my second questions is about just now you mentioned non-ventilated airspace. So based on your research, how does that affect the effectiveness of the reflective air gap? And I think one thing that you mentioned earlier, which I think no, is that if let's say the environment is dusty, over time, the ventilated airspace could cause the reflective surface of the foil that's facing the roof lah, to be dusty and then not be effective.
Yeah.
And also I think I cannot resist, as a common understanding that if you have a ventilated airspace, then the space will be cooler. So and that kept leading me to the answer that, oh, if let's say a space is ventilated, most often it will cool the internal building faster and better. So can you explain the rationale behind how a non-ventilated airspace could perform better in the reflective airspace compared to a ventilated airspace?
Okay, thank you. I think that question is quite similar to the first one, also quite similar in the
Yeah.
sense that I would say that non-ventilated airspace is actually you are reducing the convective heat transfer from happening. So it becomes sort of steady state. The airspace becomes steady state. There's no air moving here and there. Therefore, you actually reduces the convective heat transfer or the heat loss. So if you have a ventilated airspace, therefore you're introducing airflow into the airspace. By doing that, the convective heat transfer will happen. Then you will not able to reduce the radiative heat transfer. The convective will take over the radiative. So therefore, you will not become what we call a good reflective insulation, because good reflective insulation is actually to reduce the radiative heat transfer. All right. So by introducing ventilation, it actually induce the convective heat transfer. Once you have convective heat transfer, you have convective heat loss, and so on and so forth. The thermal, the reflective insulation thermal side will not work anymore. Will reduce. I think I will not say will not work anymore, but reduce in the performance. It still work, but it will not that effective.
Okay. All right.
Okay.
I understand what you mean. Yeah. But okay. So this is based on your so-called the simulation work, right?
Yeah.
The definition of why it has to be non-ventilated.
Yeah. Actually, further to add that, actually, we also found it through our experiment. During
Okay.
we have a research project. We built a test cell and then we put in the reflective insulation. And actually, we forgotten to close the fascia board. We have a fascia board open. By opening the fascia board, then the airflow can actually move through the reflective air gap. But that we met after measuring the R value, you see, hey, how come the R value is not much as what we expected? Oh, we found that the facial board was not installed by the contractor. So we asked the contractor to close the facial board. The moment he closed the facial board and we conduct another measurement, the R value went out. So it's quite significant actually.
So it is in a way.
After you run the experiment, then seeing is believing lah.
Yeah. I see. Yeah.
So that's the case of this reflective insulation.
Yeah. It is a surprising finding.
Yeah.
Yeah. Well, thanks, Dr. Lim. So the third question that I would like to ask is about the So as just now you mentioned the difference between so-called the radiant barrier and reflective insulation.
I think it's explained in the slides, right?
Yeah. But so just to get a much more clarification, because I always get confused as well. So radiant barrier and reflective insulation can essentially be made out of the same component. It's just that how you configure it to make it either reflective insulation or radiant barrier.
Correct.
Yeah.
Yeah.
So
So just to maybe recap and also to simplify it, again, reflective insulation, of course, is a system, and radiant barrier is also a system. It's not a material itself. Like mass insulation is the material itself. The R measurable, they have a R value, measurable R value. Whereas radiant barrier reflective is not a material itself. It has to be a system or assembly in order for it to perform as the building insulation. So therefore, it's a system. That means you need to have air gap, whether the air gap is ventilated or non-ventilated air gap. Okay, so if the foil, the aluminum foil is facing an open space which is ventilated, then it's called radiant barrier. When if we
Which is at the bottom.
facing, yeah, which is at the bottom. All right. So if you have a aluminum foil that faces enclosed airspace, a bounding enclosed airspace, then it's called a reflective insulation. So that is in a nutshell, if you want to bring it home with you, so that it's easier to remember.
Yeah.
Okay.
Yeah.
So that's how
I
we
hope
differentiate.
our audience, can take that away as well as a definition from the Malaysian standards as well.
Yeah.
All right. So to my last question,
Okay.
I know that your research centers around sustainable building design and technologies, which allow us to take a lot more closer steps towards achieving better buildings.
Yeah.
From your experience as a practitioner and also as a researcher, what is the biggest challenge that you face in terms of translating your research work into actual building design practices?
Okay. Very good question. And actually, most of the research that we are doing is actually mostly applied research. Applied research means is much more closer to providing solution to the industry. It's called applied research. There's also called fundamental research. Fundamental research is more fundamentals that we're looking into even the molecular structure of the material itself, tweaking the molecular structure and atomic structure. So it's very fundamental. And applied research are more closer, I would say that, because insulation industry are more concerned of the application. How does the system works and the application works and the installation methods. So that one, research, in terms of research, it can be what we call an eye opener or providing a solution to the industry. For instance, those days, people are not aware of how reflective insulation and radiant barrier works. So our research on this applied research on this reflective insulation and radiant barrier actually provide an insight into how this material perform, and give an answer to the industry in a lot of their questions. So this is a very challenging research that currently we are undertaking, and is actually very relevant to the industry. Of course, sometimes the facts that we provide might not be sometimes acceptable to the industry, but sometimes fact is facts, and we as a researcher do face that challenge to convince the industry and that this is the fact that you have to accept. Okay, so that's basically some of the challenges we face with the industry.
Yeah. Basically, what was not previously known, or rather perceived otherwise, like the ventilated or non-ventilated airspace, can be determined through actual reliable research, through either computer fluid dynamic simulation or, in your case, both CFD and also actual test cell.
Yeah.
Yeah. Thanks, Dr. Lim, for that.
Okay, you're welcome, Rocky.
Yeah. So to our next session, this is where our audience can post your questions in the Q&A box, which I will quickly post this to Dr. Lim. So we do not have a lot of time because Dr. Lim will be leaving for other appointments shortly. So let me just select a few that I think that could be relevant. Okay. So the first question, let's go with the first question, from Huan Xin. So how much difference do we expect between concrete roof and metal roof in terms of R value? So Dr. Lee, I'm not sure whether you have such study before in terms of comparing the building material itself.
Okay.
Concrete roof and metal roof.
Okay. Concrete roof and metal roof. Okay, both have different R value or U value. So of course, it depends also on the, like say for instance, the metal deck roof. It depends on your insulation material that you're going to install. So that will affect the U value and the R value as well. For the concrete roof, whereas for the concrete roof, it depends on the concrete density. The different density of concrete will have also different R value and U value. And also the finishing and also the insulation that certain concrete roof, flat roof, they also provide insulation, like for instance, bitumen, or even the torch, what I call membrane, that you put it on, that will also affect the U value of the roof. So I think this is all depends on the configuration of the roofing system. There's no what I call standard generic R value or U value for either of this roofing system. I would say that lah.
Yep.
Yeah.
All right. Yeah. Thanks for that answer, and for that question, Mansi. I hope you get your answer. Right. It depends on situation, I would say.
Yeah. Correct.
Anyway, so the next question, yeah, this is a bit tricky. Dr. Lim, maybe you can share some insight. Would the wet mass insulation due to condensation affect its effectiveness? So I would tweak a bit of the question to also ask, would say water leaking through the roof affect the reflective airspace R value?
Okay. Okay. There's two, right? One question is on the mass insulation.
Yeah.
And the other one that you're asking is on the reflective insulation.
Yeah.
Okay. So the mass insulation, if there is any condensation happen on the mass insulation, right? So if there is a water existence in the mass insulation, that one will also affect the R value. Okay, by having high humidity, or maybe during a certain time of day, there is a condensation, especially early in the morning, that water content start to stick onto the mass insulation. That will definitely affect the performance of the mass insulation. Okay, hopefully you can see look at the psychrometric chart and try to eliminate the dew point, how to reduce this the temperature from dropping below the dew point temperature. So by doing that, then you able to eliminate the condensation from happening. So that one is also important. Okay, coming to Rocky's question, what happen if there's a water leakage onto the reflective insulation or the reflective air gap? Is it what you meant?
Yeah.
Yeah, of course. Once the water drops into the reflective air gap, of course, the water will go through the air, and then eventually the water will stick onto the aluminum surface, right?
Yeah.
So I think quite similar to mass insulation, condensation can also create water, what we call existent into the reflective insulation. Of course, when that happens, of course, it also reduce the performance of the reflective insulation because of the existing of water. Okay, water can also induce what we call conduction. Conduction because it stick from one surface to another. And also maybe once the water evaporates, it invite convective heat transfer. Right. So that's why we also influence or reduce the performance of this reflective insulation.
So I would say in short, that means any sort of condensation would definitely
It's a no-no.
affect. It's a no-no, yeah.
Yeah.
And I think
Try to
the
reduce it.
way,
Yeah.
yeah, the way that the building designer can mitigate it is to refer to the psychometric chart. So typically this one is used by HVAC designers and so on. So you can
Yes.
definitely consult them.
Yeah.
I know a bit because I used to study it. Yeah, so we also covered one section where we mentioned about a psychometric chart previously as well. So you can also refer to that section. Yeah, Dr. Lim, I'll pose one last question because I know you need to rush for another session. So let me pick. Okay, from Y Bank. So are they study on the reflective insulation done on residential buildings, typically like terrace houses?
Okay. The question is, come again.
So has there been any studies of this reflective insulation done on residential buildings, like particularly, terrace houses?
Okay. I
Yeah.
would say we have not done research on the experimental research on existing terrace house, but we did build a test cell. A test cell means we also have, like, say, terrace house, we have concrete rooftops, right?
Mm-hmm.
We have concrete roof tiles, and then you have maybe mesh insulation or either reflective insulation. We did have that kind of configuration, but of course, it's not entire terrace house lah. It's on the
Mm.
test cell. Test cell. It's done on the test cell and on the field measurement. We have
Mm.
done that before. Yes.
Okay.
And that data also, we have the data also on this
Mm.
performance of concrete roof tiles compared to other roof tiles, clay roof tiles, and see the performance, the difference of the performance. And from a bit of, I'll give you a bit of review, a bit of the research findings based on this. And we also found out that actually clay roof tile, of course, perform slightly better than the concrete roof tiles because of the thermal capacity of that material itself, concrete and also clay. Clay is slightly better perform than the concrete in terms of the thermal resistance.
Mm. Yeah. All right. That means, in short, if let's say you need to, say, do more research, definitely you can, reach out to Dr. Lim, to make sure that the configuration that you want, can be, set up and tested. Of course, there will be more discussion if you need, to, set up such, experiment with Dr.
Yeah,
Lim.
sure.
So, yeah.
Sure.
All
You're
right.
welcome.
Thank you, Dr. Lim. So, of course, I think from today's session, with Dr. Lim's experience in publishing, numerous papers around, passive and low energy architecture, and also conducting so-called the building energy simulation and performance for different configuration of, building installations to achieve so-called the desired thermal comfort. I think Dr. Lim's data had shown that, what is possible in terms of research and also finding out which configuration would be the best, in our climate, right? That is the most relevant thing, in our tropical climate, right? So depending on your building design, I believe our participants can reference to this session, definitely for more discussions ahead. And at the end of the day, I think the lessons for me personally is that your decision on how to design the roof systems should be driven by properly designed experiments and actual project case studies like test out that Dr. Lee mentioned. Right. So with that, I would like to thank Dr. Lim for today's sharing, and of course, just a call out for participants who likes to present your work or your design on our platform. So you can reach out to us via this email at events@bluescope.com. All right. So again, thank you, Dr. Lim, for your sharing and your expertise. And so for architects and engineers who would like to submit your CPD points, definitely fill up the survey form. You can use your phone to scan the QR code, or you can click the link that is posted in the chat box and then submit the feedback form to us. All right. So once again, have a good day and thank you for joining Still Connect webinar.
Okay, thank you, Rocky.
All right. Bye-bye.
Bye-bye.